Vast stretches of the cosmos contain almost nothing at all. These immense underpopulated regions, cosmic voids spanning millions of light years, stand as one of astronomy's greatest enigmas. Why would a universe filled with the potential for stars and galaxies leave such enormous territories completely vacant? By the end of this exploration, you will understand 15 distinct scientific hypotheses that attempt to crack this cosmic mystery. We will investigate whether invisible forces are actively clearing space, if the laws of physics themselves are different there, and what role time and consciousness might play in this grand puzzle. What do you believe could explain these cosmic ghost towns? Invisible forces of gravity might have carved out these cosmic deserts long ago. Think of the universe not as a static painting, but as a dynamic, shifting tapestry where the heaviest objects warp the fabric of space itself. A supermassive cluster of galaxies creates a profound gravitational well, pulling everything toward it. But this immense pull has a flip side. It can also push matter away from adjacent areas, creating a kind of gravitational shadow where very little can remain. Over billions of years, these repelled regions expand into the vast voids we observe today. The mathematics behind this is staggering, involving complex simulations of countless particles interacting through gravity. These models show that tiny, random variations in the density of the early universe could be amplified into the enormous empty tracts we see now. One compelling real-world example is the KBC Void, an immense billion light-year wide emptiness that contains our own Milky Way. It is possible we live inside one of these great voids, our local group of galaxies merely a rare island in a vast sea of nothingness, pushed here by the gravitational influence of an unseen behemoth like the Great Attractor. This leads to a profound question: are we living in a cosmic backwater, a region that was cleared out by forces we are only beginning to comprehend? The very emptiness around us might be the lasting signature of a gravitational giant whose shadow we still inhabit. But what if the emptiness is not a relic of the past but an active, ongoing process? A cosmic tide is rising, and it is not made of water but of the very fabric of space. This is the domain of dark energy. While gravity pulls matter together, this mysterious force works in opposition, pushing the universe apart at an ever-increasing rate. The second hypothesis suggests that in certain regions, this repulsive force has crossed a critical threshold. Imagine trying to build a sandcastle as the tide rushes in. No matter how carefully you pile the sand, the incoming waves will sweep it all away before a structure can ever form. In these cosmic voids, the expansion driven by dark energy is so potent that local gravity simply cannot win. The attractive pull between particles of gas and dust is overwhelmed, preventing them from ever clumping together to birth new stars and galaxies. Nobel laureate Adam Rees and his team found compelling evidence that this expansion rate is not perfectly uniform. By observing distant stellar explosions, they measured how quickly the universe is stretching, and their data suggests that some volumes of space are being stretched faster than others. This variation could be written into the cosmos itself, a subtle difference in the cosmological constant, that number which represents the energy density of empty space. A real-world example of this might be the Eridanus Supervoid, a cold, barren patch in the sky. Its profound emptiness could be a direct result of its unique expansion parameters, a place where the vacuum of space has a slightly stronger repulsive character. This leads to a staggering possibility. What if these underpopulated areas are not just empty, but are realms where the fundamental rules of space-time are different from our own? The constants we take for granted might be mere local bylaws in an infinitely varied cosmos. Yet, if dark energy is actively holding these regions vacant, we must then ask what, if anything, could have originally cleared them out so thoroughly for this process to begin. The very first moments of the universe were not a smooth, placid birth. They were a storm of pure potential, a seething quantum foam where reality flickered in and out of existence on the smallest scales imaginable. This third hypothesis proposes that the great voids we see today are direct descendants of that chaotic beginning. They are the imprints of random quantum fluctuations that occurred during a period of hyper-accelerated expansion called inflation. In that unimaginably brief flash, microscopic ripples in the density of the cosmos were stretched to astronomical proportions, areas that, by pure chance, began with a slightly lower density were inflated into the vast, underpopulated regions we now observe. The theoretical work of physicist Alan Guth provides the framework, suggesting that the entire large-scale structure of our universe, from the great galaxy clusters to the immense voids between them, was seeded by these quantum events. We can actually see the evidence for this written in the oldest light we can observe, the cosmic microwave background. Data from the Planck satellite meticulously maps tiny temperature variations across this afterglow of the Big Bang. The cold spots in this map are not random. They often align perfectly with the locations of known cosmic voids, like the Draco Void. This correlation suggests that these empty regions are not accidents, but cosmic fossils. They are ancient, preserved information about the universe's wild quantum origins, frozen in time and expanded to a scale we can now measure. This leads to a staggering realization. When we point our telescopes at a dark, empty patch of sky, we might be looking at a magnified snapshot of a quantum event from the first fraction of a second of time. The emptiness is not a lack of something, but a permanent record of the universe's first breath. If these voids are indeed primordial fossils, it makes one wonder if their arrangement is purely random, or if some underlying order guides their placement. What if the great voids are not natural formations at all, but the result of a cosmic decision? This fourth hypothesis ventures into truly speculative territory, suggesting that these underpopulated regions might be exclusion zones, deliberately maintained by intelligence far beyond our own. The idea springs from the long-standing Fermi paradox, which questions why, in a universe so vast, we have not found any other signs of intelligent life. One proposed answer is the zoo hypothesis, where advanced civilizations might choose to observe emerging species like ours from a distance, much like we observe animals in a protected wildlife sanctuary. Extending this logic across galactic scales, a civilization with technology we can scarcely imagine might designate entire volumes of space as cosmic nature preserves. These would be places where nascent life is left completely undisturbed, free to develop without outside influence. The theoretical framework of astronomer Nikolai Kardashev offers a scale for such power. A Type 3 civilization, one that can harness the energy of an entire galaxy, would possess the capability to manipulate space itself. For such a society, clearing out a void spanning millions of light years might be a manageable feat of cosmic engineering. This brings us to the Lynx-Cancer void, a region noted for its remarkably spherical shape and unusually clear boundaries. In a universe where natural structures tend to be somewhat irregular, such geometric perfection is intriguing. Could this be a signature of design rather than a random product of cosmic evolution? Perhaps these areas are not preserves but scientific control zones, vast laboratories where beings experiment with the laws of physics, creating regions where constants like the speed of light or the strength of gravity are intentionally different. From our limited perspective, such technology would be indistinguishable from the natural behavior of the cosmos. This line of thinking pushes us to a profound crossroads. If we are looking at an artifact of intelligence, then the emptiness is not a void at all, but a message. It is a sign that says, "Do not enter," or perhaps "not yet." The silence we detect from these regions might be the most sophisticated form of communication we have ever encountered. Galaxies themselves could be the architects of their own isolation. Think of a young, vibrant galaxy not as a serene island, but as a roaring industrial complex. At its heart, a supermassive black hole feasts on surrounding matter, unleashing a torrent of radiation. Across its spiral arms, countless supernovae explode in brilliant, violent succession. Together, these forces generate a galactic superwind, a hurricane of energy and particles that blows outward at a significant fraction of the speed of light. This fifth hypothesis suggests these superwinds did more than just shape their host galaxies. They actively sterilized their surroundings. During the universe's most tumultuous era, these outflows acted like cosmic pressure washers, scouring nearby intergalactic space of the very gas and dust required to build new stars and galaxies. The research of astronomers like Sylvain Velu reveals how this feedback mechanism works. Radiation pressure and immense shock fronts from these events can push baryonic matter, the ordinary stuff that makes up stars and planets, far beyond the gravitational reach of a developing region. Once dispersed below a critical density threshold, that material can never collapse again. It is left as a thin, useless haze, unable to coalesce. We see possible evidence of this in places like the microscopium void. This notably empty region sits near the fossil remnants of several ancient quasars, some of the most powerful engines in the cosmos. Their furious activity, which peaked billions of years ago, might have blown a permanent bubble in the cosmic structure. The void we observe today could simply be the long-cooled aftermath of that primordial energy blast, a ghostly imprint of fury from the universe's youth. This shifts our perspective from passive emptiness to active evacuation. What we perceive as a quiet desert may actually be a battlefield frozen in time, where the birth pangs of early galaxies created deserts that would last for eons. This leads us to an even grander scale of influence, where the universe's very skeleton determines what can live and what must remain barren. The universe possesses an architecture, a grand design not of solid beams but of gravitational tendencies. This structure is known as the cosmic web, a sprawling network where galaxies are not scattered randomly but strung along shimmering filaments like dew on a spider's silk. Our sixth hypothesis proposes that the great voids are simply the empty rooms in this cosmic mansion, the vast volumes of space that naturally exist between the web's dense walls. They are the negative space in the universe's masterpiece, as essential to its composition as the brushstrokes themselves. This entire structure is predicted by our most robust model of cosmology, the Lambda-CDM model. It tells a story of how dark matter, an invisible and mysterious substance, first collapsed under its own gravity to form a scaffolding. Ordinary matter, the stuff we see, was then drawn by gravity into the densest parts of this dark framework, flowing along the filaments to eventually form galaxies at their intersections. We have seen this web come to life in immense computer simulations like the Millennium Run. These digital universes evolve over billions of virtual years, and they consistently produce a cosmic geography of clustered filaments separated by immense, underpopulated voids. A perfect real-world example is the sculptor void. This enormous region of emptiness is not a random anomaly. It exists precisely where several major filaments of the cosmic web diverge, like roads branching away from a forgotten town square. The matter was simply never dense enough there for the gravitational construction of galaxies to begin. This perspective makes the voids feel almost inevitable, a fundamental part of the cosmic blueprint. Yet it forces a deeper question. If the voids are just the empty gaps in the web, why are some of them so staggeringly large and profoundly barren, as if an entire section of the design was intentionally left blank? This structural necessity might explain their existence, but it does not fully account for their extreme character, leading us to wonder if something even more fundamental is at work within these vacant spaces. Every constant we rely on might be a local ordinance. The seventh hypothesis dares to suggest that the very laws of physics are not uniform across the cosmos, and that these underpopulated regions are deserts where the rules of reality change just enough to make construction impossible. Think of the universe not as a single nation with one set of laws, but as a vast federation where the bylaws can differ from one state to the next. In some of these cosmic states, the fundamental numbers that govern the strength of forces or the pull of gravity might be slightly shifted. Theoretical physicist John D. Barrow's work reveals how fragile our cosmic order truly is. If the fine structure constant, which controls the strength of electromagnetic interactions, were just a few % larger or smaller, the delicate nuclear reactions inside stars would fail. Carbon, the essential building block of life as we know it, would never be forged in stellar furnaces. In such a place, the universe would be stillborn, filled with hydrogen and helium but incapable of taking the next step. The mathematics behind this is profound, involving modifications to Einstein's own equations of general relativity to allow for these constants to vary across space. This tweak to the foundational code of the cosmos would dramatically alter the thresholds for gravitational collapse, raising the bar so high that galaxies could never form. A possible real-world candidate for such a place is the Orion Eridanus Supervoid. Its profound emptiness and other unusual properties could be signatures of a region where the strength of gravity is minutely weaker, or where the electromagnetic force behaves differently. What we perceive as a mere absence of light might actually be a realm with a completely different set of operating instructions. This leads to a staggering thought. We are not just isolated in space, but isolated by the very laws that make our existence possible. The voids may not be empty by accident, but by the decree of a subtly different physics. It forces us to ask, if we could travel into the heart of such a void, would our atoms, bound by the rules of our home territory, even hold together? This exploration of matter's fundamental nature pushes us to consider what raw materials might even be available in these desolate tracts, and whether the emptiness is due to a lack of substance or a substance that is fundamentally altered. The very skeleton of our cosmos might be riddled with deserts we cannot see. Dark matter, that mysterious and invisible substance, forms the gravitational foundation upon which everything visible is built. This eighth hypothesis suggests that the great voids we observe are simply the shadows cast by an even deeper emptiness, regions where the dark matter itself is too sparse to build anything at all. Think of dark matter as the hidden framework of a building under construction. Where this framework is strong and dense, workers can attach walls and windows, creating the structures we see. But in areas where the framework is weak or missing, no construction is possible, leaving only empty space. The dynamics are rooted in our most successful cosmological model, where cold, dark matter particles, moving slowly in the early universe, began to clump together through gravity. Their initial distribution, however, was not perfectly even. In regions where their initial velocity was just a fraction too high, or their density a fraction too low, these particles simply failed to coalesce. Without this dense, invisible anchor, the ordinary matter we are made of had no gravitational well to fall into. It drifted through these regions like a fine mist, never finding a place to condense into stars and galaxies. The Dark Energy Survey has provided compelling evidence for this, using a technique called weak gravitational lensing. By observing how the light from distant galaxies is subtly warped as it travels through the cosmos, astronomers can map the distribution of mass, including the invisible dark matter. These maps reveal a striking correlation. The vast cosmic voids align almost perfectly with areas of exceptionally low dark matter density. One of the most telling examples is the Capricornus Void. Studies of this region show a gravitational lensing signature that is remarkably faint, indicating an absence of mass far greater than the mere lack of visible galaxies would suggest. It appears to be a true dark matter desert, a place where the cosmic scaffold was never properly erected. This leads to a profound shift in perspective. When we gaze into a void, we are not just looking at an absence of light, we are mapping the underlying topography of the universe's invisible foundation. The emptiness is a negative image of the dark matter web, a direct readout of its most barren territories. But if these regions are defined by a lack of the gravitational glue that holds galaxies together, it forces another question. Could something be actively at work, not just failing to build, but actively dismantling and removing matter from these spaces altogether? The universe operates like a vast, self-sustaining ecosystem where matter is perpetually recycled. Stars are born from clouds of gas. They fuse lighter elements into heavier ones deep within their cores, and when they die, they seed the surrounding space with these enriched materials. This cosmic dust, rich with elements like carbon, oxygen, and iron, becomes the building blocks for the next generation of stars, planets, and potentially life itself. This ninth hypothesis proposes that the great voids are cosmic recycling deserts, places where this vital cycle has broken down or failed to start altogether. Without the heavy elements known as metals in astronomical terms, the process of star formation becomes incredibly inefficient. Normal gas clouds enriched with these metals can cool down and fragment more easily, allowing dense knots to form and collapse into new stars. A cloud of pure hydrogen and helium, however, remains stubbornly hot and diffuse, resisting the gravitational collapse that births new stellar generations. This creates a devastating feedback loop of underpopulation. No early stars means no heavy elements. No heavy elements means no efficient star formation. And so, a region becomes trapped in a state of cosmic poverty. The pioneering work of astronomers like Anna Frebel, who studies the most ancient stars in our galaxy, reveals just how critical these early elements were. Her observations of incredibly metal-poor stars show us that the very first stars formed under vastly different, more difficult conditions. Regions that missed that initial burst of enrichment, that first wave of stellar death and rebirth, were left at a permanent disadvantage. Consider the Pegasus Void. Spectroscopic analysis of the few faint galaxies within this emptiness shows a startling lack of heavy elements. It appears to be a place that never underwent the fundamental process of cosmic enrichment, a region bypassed by the cycle of stellar life and death that built the rest of the universe. This leads to a profound and somewhat melancholy question. Are these voids essentially cosmic poverty traps, where a simple lack of initial resources created a permanent developmental disadvantage, condemning vast territories to eternal emptiness? This consideration of how a region can become resource-starved forces us to confront a more violent possibility. Could a singular, catastrophic event have triggered such a barren state, effectively resetting an entire volume of space back to its primitive, unproductive beginnings. Some of the most effective vacuum cleaners in the cosmos might be completely invisible. This 10th hypothesis suggests that the great voids are not just empty, but actively cleaned, their baryonic matter systematically removed over billions of years by swarms of ancient black holes. These are not the stellar mass black holes born from dying stars, but primordial black holes, thought to have formed from the intense density fluctuations in the universe's very first moments. In certain regions, these primordial black holes may have clustered together, acting as a gravitational cleaning crew. Their method is twofold. Some matter falls directly into them, consumed forever. But a far greater amount is simply gravitationally scattered, flung out of the void like a stone from a slingshot, never to return. The theoretical foundation for this, explored by physicists like Simon Bird, shows how populations of these ancient objects could create anomalies in the large-scale structure of the cosmos. They would act as invisible seeds of emptiness, their collective gravity perturbing and ejecting the gas and dust that would otherwise form galaxies. A compelling piece of real-world evidence might be found in the Leo void. Astronomers have noted unusual proper motions, that is, peculiar movements, among the few dwarf galaxies that stubbornly remain there. These erratic trajectories could be the gravitational footprints of unseen massive objects tugging at them, consistent with a hidden population of primordial black holes drifting through the void. This transforms our view of these empty spaces from passive deserts to actively maintained clearings. The profound silence we detect might be the end result of a meticulous, billion-year-long clearance operation. If these ancient black holes are indeed the culprits, it forces a staggering question. Could a significant portion of the universe's mysterious dark matter simply be these primordial vacuum cleaners, and the voids their lasting handiwork? This idea of active evacuation leads us to a different kind of barrier, one that does not remove matter but simply refuses its entry. The cosmos might be threaded with invisible fences. Our 11th hypothesis proposes that vast magnetic fields, stretching across millions of light years, are actively shaping the distribution of matter itself. These are not the simple magnets on your refrigerator, but cosmic force fields of unimaginable scale and power, capable of dictating where galaxies can and cannot form. In certain regions, these magnetic fields could be so strong and structured that they create a form of magnetic pressure, physically supporting vast clouds of gas against their own gravity. This prevents the gas from ever collapsing to form new stars. In other scenarios, these fields act as barriers, redirecting the flow of incoming intergalactic matter like a river diverted by an unseen levee, leaving the territory behind it permanently starved of building materials. The origins of such immense fields are a mystery in themselves. They could be the amplified remnants of primordial fields from the universe's birth, or the colossal aftermath of ancient galactic superwinds, which carried magnetic fields out into the void and stretched them to intergalactic proportions. Radio astronomy observatories like LOFRR are now mapping these invisible structures. Their data reveals coherent magnetic fields that trace the very boundaries of known cosmic voids, almost like an outline drawn around emptiness. A compelling real-world clue lies in the horologium void. This immense emptiness aligns almost perfectly with one of these vast detected magnetic structures. Its profound lack of galaxies might not be an accident but a direct consequence of this magnetic barrier. This reframes our entire view of cosmic geography. The universe may be divided into territories not just by gravity, but by these invisible magnetic borders, creating a map of populated and unpopulated zones written in forces we are only beginning to see. It makes one wonder, if we could perceive magnetic fields with our eyes, would the great voids appear not as empty spaces, but as brilliantly structured, impenetrable fortresses? This idea of invisible barriers shaping cosmic destiny leads us to a final, profound dimension: the role of time itself in this grand distribution. Time itself might be the final architect of these cosmic deserts. What if the flow of time is not a universal constant, but a river that moves at different speeds in different territories of the cosmos? The 12th hypothesis proposes that these underpopulated regions are not just empty in space, but displaced in time, operating on clocks so radically different from our own that their entire developmental history has been altered. According to Einstein's theory of general relativity, time is not a separate, absolute backdrop. It is woven into the fabric of space-time and is malleable, curved by mass and energy. In a region of exceptionally low density, where the gravitational pull is minuscule, the passage of time could theoretically flow faster relative to the denser, more massive galactic clusters. The mathematics behind this involves complex solutions to the Friedmann equations, which describe the expansion of the universe, but with a critical twist, allowing the rate of time itself to vary across different cosmic volumes. In a void where time flows significantly faster, the entire life cycle of cosmic structure might have already played out. Galaxies could have formed, lived, and burned out billions of years ahead of the rest of the universe, leaving behind only cold, dark remnants that are invisible to our current telescopes. Conversely, in a void where time creeps at a glacial pace, the process of gravitational collapse may have barely begun. The region remains in a primitive, infant state, its potential for galaxy formation still locked in a distant future. The Indus Void provides a tantalizing clue. Observations reveal a puzzling distribution of redshifts among its few objects, patterns that do not perfectly align with standard expansion models. These anomalies could be signatures of temporal effects warping our perception of the region's distance and history. This leads to a staggering possibility. When we observe a void, we might not be looking at a place that is inherently empty, but at a place that is out of sync with our own timeline, a cosmic time capsule running on a different clock. From this perspective of a universe fractured in time, we are compelled to consider an even more profound dimension that might shape the cosmos, the very nature of observation and consciousness itself. Our own existence might be the very lens that distorts our view of the cosmos. This 13th hypothesis, the anthropic cosmological selection effect, proposes a startling idea. The great voids appear mysterious to us only because we are here to be mystified by them. We are not impartial observers of the universe, we are products of it, living in a very specific kind of place with very specific conditions that allowed life to arise. Our viewpoint is fundamentally biased, and this bias shapes everything we perceive as normal or anomalous. The philosophical groundwork for this was laid by physicists like Brandon Carter, who formalized the Anthropic Principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We could not possibly find ourselves in a cosmos where the fundamental constants prevent the formation of stars, planets, or carbon-based life. This logic extends to the large-scale structure of everything. The voids we find so puzzling might not be aberrations at all, but essential components of a life-permitting universe. Perhaps the stark contrast between densely packed galactic filaments and profoundly empty voids was a necessary condition for gravity to build complex structures in the first place. Maybe the presence and distribution of these voids subtly influence how dark energy behaves, creating a cosmic balance that allows for long-lived, stable galaxies like our own. Leonard Suskind's work on the string theory landscape gives this a statistical foundation. suggesting a multiverse where every possible set of physical constants exists somewhere. In this vast ensemble, we naturally find ourselves in one of the rare universes where the numbers add up correctly for life. From this vantage point, our surprise at the existence of vast empty regions is like a fish being surprised that the ocean is wet. It is the only environment the fish has ever known. The application of Bayesian probability to cosmology reveals the depth of this selection effect. We must weigh the evidence of these voids against the inescapable fact that our observations are filtered through our own existence. The profound silence of the Boötes Void, for instance, might seem like a shocking emptiness, but if a universe without such voids could never have produced us, then their existence is not a mystery to be solved, but a prerequisite of our own consciousness. This forces a humbling realization. The greatest enigma might not be the voids themselves, but the fact that we are here to point our telescopes at them and wonder. This philosophical pivot makes us question if we are over-interpreting a cosmic necessity as a profound puzzle, leading us to one final, equally mind-bending possibility. Perhaps the most profound silence is not an absence, but a transformation we cannot perceive. Our 14th hypothesis dares to ask if the great voids are not empty at all, but are instead the bustling, transcendent metropolises of civilizations that have long since evolved beyond physical form. Imagine a culture reaching a technological stage so advanced that it no longer builds cities of steel and glass, but instead converts entire star systems into pure computational energy. This is the concept of a technological singularity projected onto a cosmic scale. In such a scenario, a civilization might construct a matryoshka brain, a nested series of Dyson spheres that captures every last photon of a star's energy to fuel unimaginable data processing. Or they might take the ultimate step, uploading their collective consciousness into the very fabric of space-time, existing as pure information patterns woven into the quantum fields that underpin reality. The theoretical groundwork for such possibilities comes from futurists like Ray Kurzweil, who foresaw a point where technological growth becomes uncontrollable and irreversible, radically transforming life itself. At a galactic level, this transformation would render a region of space completely invisible to our telescopes. The starlight and heat signatures we associate with life would vanish, replaced by subtle, engineered signatures we are only just learning to look for. The energy required for such a transcendence might be harvested with such perfect efficiency that it leaves only a faint, anomalous whisper in the cosmic background radiation. A real-world candidate for this is the Boötes Void. Astronomers have noted peculiar, low-level energy signatures within this emptiness that do not fit any known astrophysical model. These could be the waste heat or the operational byproducts of energy utilization at a scale that dwarfs our entire civilization. This idea completely inverts our understanding of population. The voids we see as cosmic ghost towns could, in fact, be the most densely populated regions in the entire universe, teeming with consciousness that has moved into a phase of existence we are utterly blind to. It forces a humbling question: are we mistaking the pinnacle of cosmic development for a barren wasteland simply because we lack the senses to appreciate it? This contemplation of ultimate transformation leads us to the final and most fundamental layer of the mystery, a hypothesis that questions the very nature of the reality we are trying to observe. Our universe might be just one bubble in a frothing cosmic sea. This 15th and final hypothesis dares to suggest that the great voids are not features of our universe alone, but are the shorelines where our cosmic bubble touches others. These underpopulated regions could be interfacial zones, places where the very laws of physics begin to transition as we near the boundary of our local reality. In these borderlands, the stable constants that allow for galaxies and stars might gradually break down. Matter could be subtly leaking into an adjacent universe with different properties, or quantum entanglement with a neighboring cosmic bubble might be introducing a fundamental instability that prevents large-scale structures from ever coalescing. The theoretical foundation for this comes from the work of physicists like Andre Linde and Leonard Susskind, who developed the concepts of eternal inflation and the string theory landscape. Their mathematics describes a multiverse where countless bubbles of spacetime, each with its own unique physical laws, nucleate and expand. The boundaries between them are known as domain walls, and solving the field equations for these walls reveals they would be regions of immense tension and strange physics. A compelling real-world clue might be the famous CMB cold spot, a strangely frigid patch in the cosmic microwave background that correlates with the location of the Eridanus Supervoid. This anomaly could be the signature of such an interface, a place where the energy of our universe is subtly draining into a neighboring cosmic realm. What if these voids are not empty at all, but are instead cosmic windows, places where the fabric of our reality grows thin enough to glimpse the utterly foreign physics of another universe entirely? From our perspective, it appears as a barren desert, but that emptiness might be the most profound evidence of a greater multiverse lapping at our shores. Having journeyed through these 15 distinct explanations, from gravitational shadows and dark energy to cosmic engineering and multiversal shores, a collective truth emerges. The mystery of the great voids is not a single puzzle with one solution, but a multifaceted enigma that probes the very limits of our understanding. Each hypothesis, from the most conventional to the wildly speculative, illuminates a different aspect of our cosmos, whether it be its past, its physics, or its potential. They reveal a universe that is far from uniform, a tapestry of incredible variation where emptiness is as meaningful as presence. These silent, dark regions challenge us to think bigger, to question our assumptions, and to remain humble in the face of a cosmos that continues to guard its deepest secrets. This grand tapestry of cosmic emptiness reveals its deepest secrets not through isolated threads, but through their intricate weaving. The gravitational shadows cast by ancient galaxy clusters might have provided the initial blueprints for these voids, which were then maintained and expanded over eons by the relentless push of dark energy. The primordial quantum fluctuations from the universe's first moments could have dictated where these empty regions would one day appear, their locations forever imprinted on the cosmos like a hidden watermark. Within this vast architecture of the cosmic web, all other mechanisms find their stage, their interplay creating the complex pattern of fullness and emptiness we observe. The more speculative ideas, from transcendent civilizations to multiversal shores, serve a vital purpose. They challenge our very definition of what it means for a region of space to be populated. We are forced to confront the possibility that our search for light and heat might be as provincial as a hunter-gatherer scanning the horizon for campfires, completely missing the bustling digital cities beneath their feet. This is where the Anthropic Principle binds these disparate ideas into a coherent whole. The existence of these vast voids, shaped by the combined effects of gravity, dark energy, and quantum history, might not be a cosmic error but a fundamental requirement. Perhaps a universe without such profound contrasts and empty expanses would lack the precise conditions that allowed for long-lived, stable galaxies and ultimately for us to gaze upon them. The silence we ponder is not a void in meaning but a necessary silence, the quiet backdrop against which the symphony of cosmic structure could play out. This integrated view does not solve the mystery so much as transform it. suggesting that the true nature of these underpopulated regions can only be understood by appreciating their multifaceted role in the cosmos. They are at once a relic of the past, an active component of the present, and potentially a key to our future understanding of reality itself. Our journey through these cosmic deserts reveals a universe far richer in questions than in certainties. We have stood at the edge of profound emptiness, guided by 15 distinct lights, from the gravitational shadows of ancient giants to the whisper of dark energy and the faint echoes of quantum birth. Each hypothesis, whether rooted in established physics or soaring on the wings of speculation, does not cancel out the others. Instead, they intertwine, creating a multifaceted portrait where emptiness is an active, evolving component of the cosmos. The true lesson may not be which idea is correct, but how collectively they expose the limits of our current gaze. Carl Sagan's reflection that the universe seems merely indifferent finds a deep resonance here. In the grand, silent voids, that indifference is not a void of meaning, but a blank canvas for our curiosity. These regions compel us to build better telescopes, to question our most fundamental assumptions, and to remain humble before the sheer scale of what we do not know. It is a profound thought that the empty spaces between the stars might ultimately teach us more about reality than the shining galaxies themselves. I am deeply curious to know which of these possibilities speaks to you. Was it the cosmic feedback of galactic winds, the haunting possibility of transcendent civilizations, or the stark beauty of the Anthropic Principle? Share your thoughts in the comments below, and if you wish to continue this journey to the edge of understanding, subscribe as we prepare to venture even deeper into the quantum foundations of spacetime itself.